We will do an interesting experiment today. Taking a tub, we fill it with plain water and also add some little color to it so that we can see it properly. Now we will take a glass in which we fill this water and invert the glass above the water surface, and the water drops down below. Why? Of course, because it is being pulled down by gravity. It has its weight, which is an indicator of the pull of gravity, because of which it comes down. Now we will do a variation of this. We will fill the glass now below the surface of water. So I will take it in, fill it up with water below the surface and invert it below. And now I try pulling it up. Now, as I bring it up, water is filled up inside the glass. It must be having its weight pulling it down, but the water does not fall. I pull it up slowly, more, and suddenly, as soon as the edge of the glass leaves the water surface, the water drops down below. But why was it not falling it before? After all, there must be weight, there must be gravity pulling it. So what was actually supporting this weight? Something must be countering this weight, some other force, because of which it was holding up, and that is what we have to find out. Suppose we take a larger container. So this time I am taking a very large container which will have at least 2 liters of water inside. I fill it up below the surface and I invert it and try bringing it up. So slowly, as I pull it above, there's a lot of water filled up inside. It comes up, but that water having a lot of weight. I can feel it in my hands. As I hold the glass cylinder, I feel it, but the water is not coming down. Gravity is pulling it, but it is not coming down. I bring it up still further and still further and still further. The water does not drop in spite of having a lot of weight. And now it suddenly comes down as soon as the rim leaves the edge of water. So suppose I take an even taller container, a measuring cylinder, which is pretty tall, and repeat the same thing. Once again, I see a big column of water holding up and not dropping down below when I pull it up. So what is holding this water up or supporting its weight is the question we have to ask. Another question we have to ask is, how long will this go on? Till we make our water column 1 meter, 2 meters, 10 meters, 100 meters. How long will it hold up? Will it hold up forever? So this is something we have to see experimentally as we make our glass column taller or water column taller. So we have to see how much we are able to take it further. If I show it on a diagram, I have a container full of water above, which is full of water, so there is a weight of the water acting downwards as a force. So to counter this weight, this force has to be supported by something in the opposite direction for this to be holding up. And what is that other force is the question which we are asking, and a scientist asked nearly 400 years back. His name was Evangelista Torricelli in 16th century. He asked the same question, what is holding the water up? He observed something very, very interesting, which is he saw that in their pumps, so they had like pipes pulling water up from wells from below, and first air was pulled up using a suction pump, the way we do in a hand pump today. There was no electricity at that time. So air was sucked out and the water climbed up. But he saw that water does not climb beyond a certain height. So, and the theory at that time was that low pressure or partial vacuum was pulling the water up. But then water did not climb beyond 10.3 meters or 34 feet, even if we sucked out a lot of air. So then the vacuum pulling above or low pressure pulling above did not hold. There had to be something else. So Torricelli hypothesized that there is a lot of air above us. It's a sea of air. It must be having its own weight and it must be pressing down on everything below with force per unit area, which we call as pressure. So this is air pressure or atmospheric pressure which presses the surface of water, and then the water inside the bowl has all this pressure acting and pushing water above the column of water, above the tube if we take out some air from the tube. If we evacuate the tube, the water is pushed up because of this pressure pushing it above. So it is this pressure into the area which is the upward force shown with a red arrow, which is actually countering the weight. So that it was Torricelli who said that it is atmospheric pressure which is holding this column of water above. So he tried an experiment with mercury because mercury is far denser than water. So he could take a smaller tube, not something taller than 10 meters. He took a single 1 meter, filled it up with mercury and inverted it in a bowl of mercury. Once he inverted, the mercury dropped by itself, but it stopped at a particular height, and at 76 centimeter, the mercury column stayed. So the weight of all this mercury was being supported by the air pressure pressing down on the surface of the mercury in the bowl. And so Torricelli said the height of this mercury column is actually showing us the measure of the atmospheric pressure. How much atmospheric pressure is there and how much mercury it can hold. So this device became a measurement device for measuring atmospheric pressure and is called the Torricelli's barometer. The principle is that the atmospheric pressure holds the column of liquid in the tube, and this is the barometer principle or Torricelli's barometer.